Hi, and welcome to the video on learning how to divide polynomials using synthetic division. Let's get started. All right, so in our previous section, we were able to find zeros of polynomials by factoring, but sometimes if we have higher degree polynomials, it's really difficult to factor, so we need a new tool, and that's called polynomial division. Our first couple examples, we're not going to need polynomial division. We're just going to be able to use properties of exponents. I just want to remind you about that, and then we'll jump into polynomial division. So our first example is x to the fourth divided by x squared. So let's just, oh, what did I do? Hang on. X to the fourth divided by x squared. So we're just going to go rewrite this as x to the fourth over x squared. And we can remember by properties of exponents as x to the 4 minus 2, which is x squared. So 4 of the x's in the numerator cancel 2 of the x's in the denominator. Let's go on to example 2. In this example, we have x to the ninth plus 2x to the 7th minus x to the 4th all over x cubed. Now, when you're dividing this problem, you need to remember that this x cubed is going into all pieces of this polynomial. So when we go to simplify this, we're going to write it as x to the ninth over x cubed plus 2x to the 7th over x cubed minus x to the 4th over x cubed. And now simplify these. X to the 9 minus 3 is x to the 6th, plus 2x to the 7 minus 3, which is 4, minus x to the 4 minus 3, which is 1, so just x. x6 plus 2x to the 4th minus x is our simplification. So if the denominator, when we're dividing, is just a single variable, we can use properties of exponents to simplify. But if it's a longer polynomial, we have to have a new tool. So just a word about polynomial long division. We won't be doing that in our class. If you like that and have done it in other classes, that is fine. I'm not going to stop you. There's also some videos on that in the helpful video section of our Canvas. However, we're just going to be using synthetic division in this class. So synthetic division is just a way of dividing polynomials when the denominator or the divisor is of the form x minus a number. So if you're dividing off a single linear factor. So here's our first example. 5x squared minus 3x minus 36, and we're going to divide that by x minus 3. So to do synthetic division, you set up a chart like this, and in the top row, you're going to put the coefficients of the number, the polynomial that you're dividing into. So 5x squared minus 3x minus 36. So those numbers go there. The number that goes here to the left is the root. So if x minus 3 is our linear factor, that means 3 makes it 0. 3 is the root. Be careful because it's always x minus the root. So 3 goes here. And to do synthetic division, you just follow this algorithm. First, you bring down the first number, which is 5. Then you take 5 times 3 and you write it in this space. You add down. Minus 3 plus 15 is 12. Then you multiply 12 by 3 and you get 36. Minus 36 to add 36 is 0. So that's the process. You multiply, add down, multiply, add down. If you get a 0 in this last column, this is your remainder. So getting a 0 remainder means that it divided evenly. So that means that x minus 3 divides evenly into 5x squared minus 3x minus 36. Let's get into that a little bit more. So if we look about what else is left over here, we have a 5 and we have a 12. This is my constant term, and this is my x. And then if I had more, I would keep going up. So what this tells me is that if I take 5x squared minus 3x minus 36, and I divide it by x minus 3, it would be 5x plus 12. Or x minus 3 times 5x plus 12 equals 5x squared minus 3x minus 36. So because if you divide that 5x squared minus 3x minus 36 by x minus 3, and you get 5x minus 12, that means that those things multiply together to get the original value. Let's try another example. Just practicing the synthetic division. All right, so we're going to set this one up. It's a little bit longer problem. We're going to write our coefficients, and make sure you put these in order of decreasing degree. So I don't have an x term here. I have x fourth, x cubed, x squared. I don't have an x, and I have a constant. So that means I need to put up 0 placeholder for my x term. So negative 9, 10, 7, 0, negative 6. So that's my constant, x squared, x cubed, x to the fourth. And again, my linear factor is x minus 1, so that means my root is 1. All right, let's go through the synthetic division process. First, you bring down the negative 9. Negative 9 times 1 is negative 9. 10 plus negative 9 is 1. 1 times 1 is 1. 7 plus 1 is 8. 8 times 1 is 8. 0 plus 8 is 8. 8 times 1 is 8. And negative 6 plus 8 is 2. So this time I did get a remainder. That means it doesn't divide easily. It doesn't divide evenly. So that means that 1 is not a root of this polynomial because x minus 1 doesn't factor out of it. Because if 1 was a root, then x minus 1 would factor evenly out of it. But we did do the synthetic division on it. All right, let's keep going. So we're going to use synthetic division now as a tool to help us completely factor higher degree polynomials. So here's the polynomial that I want to find all my zeros of. It's f of x equals 6x cubed minus 49x squared plus 46x plus 21. Now, we graph this in Desmos, and I just pasted that here, and we can see from the graph that it has 3 real roots. We have one here, and one here. Now, these first two are kind of in between. It might be negative a half, it might be 1 1/3, I'm not exactly sure, but I can see that this one is hitting right at x equal to 7. Okay? So since I can't find the other two easily, I'm going to start with the 0 that is 7, and I'm going to divide x minus 7 synthetically into my polynomial. So I'm going to divide f of x using synthetic division by the linear factor x minus 7. So 6x cubed minus 49x squared plus 46x plus 21. And I had terms for each of the powers of x, so I don't need any placeholders. My root is 7, so 7 goes here. All right, so 6 comes down. 6 times 7 is 42. Minus 49 plus 42 is negative 7. Negative 7 times positive 7 is negative 49. Negative 49 plus 46 is negative 3. Negative 3 times 7 is negative 21. 21 minus 21 is 0. And that's good because since we know 7 is a root, we know we should get a remainder of 0. And what this tells me is that x minus 7 times minus 3 minus 7x 6x squared is a way to factor this polynomial. So I'm going to write it down. X minus 7, my linear factor that I divided off, 6x squared minus 7x minus 3. If I multiply that all out, I get back to my original f of x, which is 6x cubed minus 49x squared plus blah, blah, blah. All right, so we were able to reduce a cubic polynomial to a linear times a quadratic. So now all we need to do is we need to factor this, we need to factor the quadratic term. So how do we factor that? Well, we can use the AC method. Right? So the AC method says our A value in this case is 6. Our C value is negative 3. So A times C is equal to negative 18. And now we need to think of two numbers that multiply to negative 18 and add to this middle term, which is negative 7. So I think that's negative 9 and positive 2. So x minus 7, and then we rewrite this, 6x squared. So we're going to use negative 9 and positive 2. Minus 9x plus 2x minus 3. And if you have a different way that you'd like to factor quadratics with non-one leading coefficients, go ahead and use it. You don't have to use the AC method. All right, now we're going to group our terms. So we group, 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 group. This gives us x minus 7. In this first grouping, we have a common factor of 3x. And that leaves behind a 2x, 6x squared, minus 3. And in this one, we don't have any common factors, so we're just going to write down a 1 as a placeholder. There's no common factors between 2x and negative 3. What happened here? 2x minus 3. And now we have this x minus 7 still coming along from the ride. We can factor 2x minus 3 out of each of these. Oh my goodness, what happened? I bumped something. We can factor 2x minus 3 out of both of these. Why? Okay, what did this just quit? Where we go? 2x minus 3. And that leaves behind 3x from the first term plus 1 from the second term. So now we're completely factored. And we know using our zero product property that this root was x equal to 7. We could see that one on the graph. To make this 0, we would put in 3/2. And we saw that one, so that must be 3/2, right? And to make this 0, we would put in -1/3. And that must be this one. So we found all 3 zeros by dividing off the one root, the 1 0 we could find, reducing a third degree polynomial to a quadratic, and then we used factoring methods to find the remaining 2 zeros. All right, let's do one more example here. We're going to do, this one is going to be a little bit more complicated because we're going to have some complex roots as well. So remember, we went over complex numbers, and now we're going to completely factor this polynomial h of x, and we are given that one of the roots is at x equal to -1. So we don't have a graph. We don't have to graph it. They're just telling us right off the bat there's a root at -1. So I'm just going to start using polynomial long division, synthetic division. 1 minus 1, 8, 10, and the root is -1. So I'm going to divide the linear factor x minus -1 off. That will reduce this third degree polynomial to a quadratic. In that case, I can use quadratic formula or factoring or whatever. Bring down the 1. -1 times 1 is -1. -1 plus -1 is -2. -2, -1, +2. 8 plus 2 is 10. 10 times -1 is -10, and good, we got a 0. If you're dividing by and you know it's a root, you have to get a 0 remainder or you did something wrong. So this polynomial is x minus our root, -1. That was what we divided by, and we get, this is my x, and this is my x squared minus 2x plus 10. So let's rewrite this as just x plus 1, because that's easier to look at. X squared minus 2x plus 10. So now we can try to factor. Can we think of two numbers that multiply to +10 and add to -2? Well, we could go 1 and 10, but that doesn't add to -2. We could go -2 and -5, but that adds to -7. So no, there aren't any numbers that are going to be able to factor this. So I'm going to have to use the quadratic formula. So let's go ahead and just plug it into the quadratic formula just on this quadratic. So x equals, let me just draw a little squiggle here, -b plus or minus the square root of b squared minus 4ac all over 2a. So that's 2 plus or minus the square root. That's going to be 4. Excuse me. 4 minus 40 all over 2. So that's 2 plus or minus the square root of -36 over 2. Keep going. 2 plus or minus the square root of -36 would be 6i all over 2. So we take 2 into both of those and we get 1 plus or minus 3i. So as our two roots. So when it's asking us here, what are all the zeros of h of x? We have one real 0. X equal to -1, and we have two complex zeros. And that's x equal to 1 plus 3i, x equal to 1 minus 3i. Now remember, we're always going to have, now that we are allowed to use complex numbers, now that we know how to use complex numbers, we're always going to have to account for all the zeros matching the degree. So if it's a degree 3 polynomial, you're going to always have 3 zeros. Now, you might have 1 real and 2 complex, or you could have 3 real, or you could have a double root at 1, but you're always going to have to account for all those zeros. All right, so that's synthetic division.